Hi everyone. Today we're going to take a look at the day 5 notes, which bring up a very important topic in Calc C, which is Taylor series. Before we do that, I'm going to go back to the last notes because I want to talk about a really important idea from the very last example, example 4. Okay? And it's kind of right at the end here, right? This idea of we ended up with getting the function arctangent of x as our answer, right? And saying that arctangent of x or tangent inverse of x could be represented, right, as this function, right, infinitely, right? X minus 1/3 x cubed plus 1/5 x to the fifth minus 1/7 x to the seventh plus dot 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 dot, right? This power series, right? Because these are, right, we're multiplying powers of x to get the next term, right? This power series can be used to represent another function, right? This infinite power series all adds up to some other function that we know and love. Okay, so we're going to carry this idea into our notes today. So this opener part, right, is just kind of recapping what we did in that last example, right? Again, arctangent of x, right, can be rewritten as this infinite power series, right? And remember, a power series is just a geometric series, and we're multiplying powers of x to get the next terms, okay? So arctangent of x is one of these functions that can be represented with a power series. Well, it turns out there's a lot more functions that can be represented with a infinite power series, right? And example 1 has us talk about a very important one, okay? E to the x, right? Find a power series that approximates e to the x centered about x equals 0, okay? And so basically what we're looking for, right, is we're looking for this idea of what function, or sorry, e to the x is the function, right? How can I represent it as some constant times x to some power, right? Now, if we think about this with the arctangent example, right, we know that, okay, maybe the constant is 0, or maybe some of the terms, the coefficient is 0, right? If we go back and look again at what we did in example 4 on the last notes, right, there was no constant in front. There is no x squared term. There is no x to the fourth term. Well, technically they are there, right? It's just that the coefficients are zeros, right? Okay, so that's what we're going to try to find, okay, right? So we're going to try to find what all of these coefficients are that go in front of all of these powers of x, okay? So we want it centered at 0, so that's why it's just x and not quantity x minus a, right? Which is, again, something we covered in the last note sheet, okay? Now, how do I find infinitely many coefficients, right? Because technically it takes infinitely many terms to add up to get to e to the x. Well, the beauty of math is that there is a pattern, right? We're not going to find infinitely many. We'll find a bunch, right? And hopefully we'll pick up on what the pattern is so that we can write a shorthand for e to the x. Okay, so the first one we're going to find, c sub 0, is the only term that doesn't have an x in it, right? So I can get rid of the rest of these terms if I let x be 0, right? So if I do f of 0, I get e to the 0, which is 1, which will drop all of these terms with an x, and so I would get just that c sub 0 is 1. So the very first coefficient, right, is a 1. Okay, now I want to basically try to figure out a way that I can drop the rest of these terms and then plug in 0. Excuse me. So the way I'm going to do that is I'm going to start taking derivatives. Okay, so you're going to see how this works. So what's f prime of x? Well, beautifully, for e to the x, it is itself. Now, for any constant, the derivative is 0, so c sub 0, which again we know is 1, goes away. C sub 1 times x to the first, right? Well, that's just going to be c sub 1. And now, for the rest of the terms, we can just apply the power rule, right? But here's the beauty. Now c sub 1 doesn't have an x with it, right? Which means I can go ahead and plug in 0 for x. E to the 0 we know is 1. When I plug in 0 for x, the rest of these terms will drop out, and I get that c sub 1 is 1. Okay, now some of you might be thinking, are all the coefficients just going to be 1? No, they're not. If I take a look at what my f prime was for the terms, right, let's do another derivative. Let's do f double prime, which again, for e to the x is itself. C sub 1 derivative is 0. For 2 times c sub 2 times x to the first, the x goes away. The rest of the terms, I do the power rule. Excuse me. And now, if I plug in 0, f double prime of 0, so e to the 0 is again 1, but this time it's going to equal 2 times c sub 2. So again, I'm plugging in 0. That's getting rid of all of the terms that still have an x in them. 2 times c sub 2, so c sub 2 is going to be a half. Let's keep going, right? Let's take my f double prime, right? Let's take its derivative. That would be f triple prime. E to the x, right? So 6 c sub 3 times x, so the x goes away. For the rest of the terms, do the power rule. All of the rest of the terms have an x, so I plug in 0 into the function. E to the 0 is 1. 6 times c sub 3 is all that's left, because the rest of these terms with an x are all going to drop away, right? And so I can solve, and I get c sub 3 is 1/6. I'll do this one more time. Take my f triple prime. Let's take the derivative, right? The fourth derivative of f of x is e to the x, right? And so all I would be left with for terms that don't have an x is 24c to the fourth, right? Every other term, I keep doing the power rule, right? If you're wondering where these coefficients are coming from, go back to the start. Just follow your power rule, right? How do I get these terms, right? I have c sub 4, x to the 4. Okay, great. We bring the 4 down. Next time it's x cubed. Okay, so I bring the 3 down. It's a 12. Now it's x squared. Bring the 2 down. So it's a 24, right? You can follow this pattern every time, right? And that's how we get this, okay? And so, but every time I plug in 0, e to the 0 is 1, right? So I'm just dividing that over. I get 1 to the 20, or excuse me, 1 over 24th. And now this is where you have to put your beautiful brains together, right? C sub 1 is 1, C sub 2 is 1/2, C sub 3 is 1/6, C sub 4 is 1 over 24. What's the pattern? Clearly the numerator is just a 1, right? But what is happening with these denominators, right? So if I think of the first one here as 1 over 1, so it goes 1, 2, 6, 24. How am I getting this every time, right? What I'm doing is I'm taking the denominator of the previous one, multiplying it by the n on the next one, right? So over 1 times 2 times 3 times 4, etc., etc. Now, what do I get if I just keep multiplying integers together, right? Dun, 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 dun. We get factorial, okay? Right? Each previous one is just being multiplied by 1 over n, right? 1/6. I want the fourth one, I multiply by 1/4, right? The previous one multiplied by 1 over n, but the shortcut for that is that it is just n factorial. Okay, so let's bring all of this back. All of this was try to come up with a series to represent e to the x, right? And so my c sub 0 was 1, my c sub 1 was 1, my c sub 2 was 1/2, c sub 3 was 1/6, c sub 4 was 1 over 24, and the general pattern is that c sub n is 1 over n factorial. So that means my c sub 5 would be 1 over 120, because that's 5 factorial. 6 factorial would be 720, etc., etc. And now we have an infinite series that represents e to the x. Now, this may not surprise you or impress you in any way, okay? But this is kind of freaking incredible, okay? Right? Because we think of e to the x, right? We go, oh yeah, derivative is the same, that's cool, right? But I want you to think back to the late 1600s, 1700s, 1800s, when there are no calculators, right? And you want to know, hey, what's e squared, right? What is that 2.71828 blah, 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 right, times itself, right? That's kind of hard to multiply when e goes on infinitely, right? But if you pick enough terms, all you got to do is plug in 2 for x, and you can approximate what it is. And now you might go, hey, that's kind of annoying to add up, but adding fractions, right, is a heck of a lot easier than multiplying infinitely many numbers together, right, to calculate something like e squared. Okay, so I'll get off my soapbox. Let's go ahead and summarize. E to the x, represented as a power series, right, is from 0 to infinity, x to the n over n factorial, right? So what's the r value? What's getting multiplied every time? We're adding, or not adding, we're multiplying a power of x to the top, x to the 0, to the first, squared, third, fourth, etc. But to the denominators, we're multiplying n, right? So technically, right, don't forget this initial one is 0 factorial times 1 times 2 times 3 times 4, etc. So x over n is my common ratio, right? Again, in order for this to converge, right, this must be less than 1. But here's the thing, right? I'm going to have infinitely many terms, right? If let's just say I want to use this to approximate e squared, the x is fixed, right? N is going to go to infinity, right? Because the more terms I add, I need to add more terms to get more accuracy, right? So x is fixed while n goes to infinity. So what this means is that if I think of it like a limit, right, this is going to always converge because this, my common ratio, is always going to be closer to 0. Okay, so again, if I want to use this to approximate e to the fourth, all of these x's get replaced by a 4, right? But the number of terms goes to infinity. Think of it like 4 over a million, billion, trillion, right? So this is going to always converge. Okay. Okay. So this brings us to the idea of the Taylor series. Okay. And e to the x was the perfect example to start with this, right? So let f of x be an infinitely differentiable function, just like e to the x, on an open interval containing a. So a is just going to be where we center it, right? So this one, right, we wanted to center at 0, but we could center it anywhere, right? We talked about this in the last notes. It's just kind of like shifting, okay? Pardon me. The Taylor series generated by f of x at x equals a is, right, it is going to be f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a to the third, right? And you would do this infinitely, right? And that's exactly what we have up here, right, with e to the x. Okay, right? And we can represent this in sigma notation as well, right? But again, all of this is only applicable to certain very specific functions, right? Infinitely differentiable function, right? So if you think about it, right, could I do this for, something like sine of x? Yes. Eventually, sine, the derivative will loop back to being sine of x, but it is infinitely differentiable, okay? And now could I do this for something like, let's say f of x was x squared. Is x squared infinitely differentiable? Yes, but eventually all your derivatives become 0, right? And so the rest of the terms drop out, right? So doing something like this for a polynomial isn't really worthwhile, right? But we can do stuff like this for functions like e to the x, and we actually already did this for tangent inverse, and we'll do this for some more in the future. One more vocab word to throw in here, sorry, is this idea of a Maclaurin series. Okay, a Maclaurin series is just any Taylor series centered at 0. So technically what we found for e to the x is a Maclaurin series. So that's just a subset of Taylor series. Okay. Okay. So let's go ahead and use our answer here for e to the x, our Taylor series or Maclaurin series for e to the x. Let's try to use it for an approximation. Example 2. Use a degree 3 Taylor polynomial for e to the x centered at the origin to approximate what f of 1 is. Now, f of 1 is just e to the first. We know that's just e, right? Excuse me. So we know the decimal is 2.7182818, blah, 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 blah. Okay? But how good could we have made an approximation before we had electricity in the world? Well, let's take a look. Okay? So my function is e to the x, right? Now, a little bit of notation here. I'm approximating e to the x with p3 of x. P3, right, is short for my degree 3 Taylor polynomial. Degree 3 does not mean 3 terms. It is as many terms as it takes until I get to the x cubed term, right? So for e to the x, it was 1 plus x squared over 2 plus x cubed over 6. So again, I use the approximation symbol here, right? I am approximating e to the x with this degree 3 Taylor polynomial. And now I want to approximate what f of 1 is. So f of 1 is e to the first is approximately p3 of 1. So I replace all of these x's with a 1, and now I add all these together, right? And so I get 2 plus a half plus a sixth, right? That is 8/3, which is 2.6 repeating, right? Compared to, again, the actual answer we know is 2.718, blah, 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 right? And so before there was electricity in all of our houses in the world, right, we could have approximated this, within, just not off by more than really a tenth. Okay, pretty impressive. Okay, let's go ahead and find another Taylor series. Let's do it for Sine of X. Example 3, find a Taylor series for Sine of X centered about the origin. Okay. Pardon me. All right, so Sine of X, right, centered at the origin. So we start with f of 0 plus f prime of 0 times x minus 0 to the first plus f double prime of 0 over 2 factorial times x minus 0 squared plus f triple prime of 0 over 3 factorial times x minus 0 to the third, dot, 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 dot. This would go on, okay? Now, you could go ahead and find all these values. You're all very capable of that. But one thing I recommend is, again, trying to look for some patterns, okay? So instead of trying to just do them individually, right, I went ahead and made a table. So a couple of things I want to know, right? What is the nth derivative of my function? And then what is the nth derivative of f at 0? So the first derivative of sine is cosine. Then it's negative sine. Then it's negative cosine. Then it's sine again. And then we know the cycle repeats, right? We're back to cosine. The fifth derivative of sine is the same as the first derivative of sine, right? Now, plugging in 0, this is just unit circle time. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. And then, again, it's going to repeat after that. Okay? And so, what's going to happen here, right, is sine of x is going to be 0, because that's my f of 0, plus, right, 1 times x, right, because 1 is my first derivative, so that's times x to the first. And if it helps you, you can always write this over, right, 1 factorial, if that helps you out for that first term, okay, and memorizing the general Taylor series formula. All right, but then from there, right, every even term, right, when n is even, right, I'm always going to get 0 for the derivative. So the x squared term goes away. The x to the fourth term goes away, right? And so what I'm left with for sine of x is all of the odd terms, right? Starting with x, right? And then we alternate signs because if you look at the pattern for the odd ones, it's going to be 1, -1, 1, -1, etc. So we're going to have x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial minus x to the 11th over 11 factorial plus, and this goes on forever. I can go ahead and represent this using sigma notation, right? So starting at 0, right? Now, really what I'm doing, though, is I'm not going to represent all of the terms that went away, right? I'm just coming up with a notation for the terms that remained here, right? So when n is 0, right, the first term should have an x to the first. So that's why I use this 2n plus 1, right? 2n plus 1 for any n value is guaranteed to get you an odd number, right? So when n is 1, 2 times 1 plus 1, that's 3 over 3 factorial, right? That's how I get the second term. N is 2, 2 times 2 plus 1, that's going to get me 5, right? That's how I get this term right here. Okay. So all of these are geometric, right? What am I multiplying? I'm multiplying each term by -1, right? I'm also multiplying by an x squared, and I'm also multiplying by, and this part gets a little weird, right? If I have 1 factorial to 3 factorial, so I'm multiplying by the 2 and the 3 factorial, right, which are the next two terms. So from 3 to 5, I'm multiplying by 4 and 5. From 5 factorial to 7 factorial, I'm multiplied by 6 and 7, right? So I'm multiplying by 2n and 2n plus 1, right? The two biggest terms, right? That's how I get the next one, okay? Now again, just like with e to the x, n is going infinite, right? And so x is fixed, right? And so this is going to always converge because my ratio is always going to be less than 1, right? So if I want to use this to approximate sine of pi, right, I would use, right, infinitely many terms in my sequence. So, I could put in pi for x, but n is going million, billion, trillion. Okay. Okay, so we're going to take a look at group problem 1 now. Okay, so let f of x be an infinitely differentiable function for all real numbers, right? And we are told some derivative values of f without being told what f is. So this is a good AP type of question here. Okay, f of 1 is 2, f prime of 1 is 1, f double prime of 1, -2, f triple prime of 1 is -3. Write the third order. So order is another word for degree. Taylor polynomial for f of x at x equals 1. So good thing they're telling us for x equals 1, right? Because all my derivative values are at 1, so that's good. Okay, so I'm going to approximate this f of x with, again, p3 of x. So that's going to be f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared plus f triple prime of 1 over 3 factorial times x minus 1 cubed. And that's where I stop, right, because I'm going third order or third degree. Okay. And so I can go ahead and plug in all of my derivative values that I was given, right, for all of those. And then I can just go ahead and simplify. And once I have this, right, I'm going to approximate f of 1.2 by plugging in 1.2 into P3, right? So I replace all of the x's, right, and I get my approximation, which is 2.156. Okay, last one, group problem 2. Find the Taylor polynomial, again, of order 3. So I'm looking for P3 again. of a different function. Okay, that's kind of weird. All right, x cubed plus x minus 3. It's a polynomial, but we can still come up with a Taylor polynomial. Okay, so, oops, I'm sorry. Centered at x equals -1, so that's important. Okay, so the first thing I need is what is f of -1, right? So I go ahead and do that. And now, folks, I really, really recommend kind of organizing your work well, almost like making a table, right? So on one side, I write the function, the derivative function, then I get my derivative value. Derivative function, derivative value, derivative function, derivative value, and now you just have to remember how the formula goes for a Taylor series, right? So, and this is the first thing I did in my work, is I rewrote that formula. P3 of x is going to be f of -1 plus f prime -1 times x plus 1, because double negatives, right? Plus f double prime -1 over 2 factorial over x plus 1 squared plus f triple prime -1 over 3 factorial times x plus 1 cubed. And now it's just a matter of plugging in my derivatives and simplifying my factorials. And now you could keep simplifying if you want, okay? But there you have it, all right? And that's it for now. I'll see you next time where we're going to talk plenty more about Taylor series.